Okay, so this is a quick description about how we can describe a population statistically. So let's just say you go out and you are supposed to sample a forest. There are a really high number of trees in this forest. And so realistically, you can't measure every single tree in the forest. So what you naturally do is subsample. And say you take a few randomly selected samples, and out of the million trees that happen to be in the forest, you end up sampling, let's say 1,000. So you only sampled 1/1000th of the population, but what you're assuming is that this distribution, and we're just going to say you measured the size of 1,000 trees, what you're going to assume is that this distribution of tree size, whatever that is, and this is frequency, is an approximation. This is 1,000 trees, is an approximation of this actual distribution. That if you did your sampling correct, both of these, the actual number you measured and the real total population that you're subsampling from, are going to have the same mean. And so if you look at this distribution, the center is the mean. And so we're assuming that they have the same center mean and that the width of the distribution is about the same. So this width we're going to call the variance, or we're also going to describe the width as the standard deviation. Okay, so at this point we can assume that every time we go out and try and estimate a total population size, that's not likely to be realistic, and so we can subsample from populations and estimate what the real population looks like statistically. Now, the other thing that's important to note is that here you're sampling, say, 1,000 individuals. One thing that is really convenient about using a mean and standard deviation is you can take that quantity of 1,000 individuals and summarize it with just two numbers. So you can take 1,000 individual data points and summarize in just two numbers, which is really convenient and will be really important for comparing different populations. So let's talk about calculating some of these numbers. So calculating the mean, we have to get into some notation that's going to be important. So this symbol, x with the bar on top, is going to be what we use to call the mean. And in sort of math notation, the mean can be symbolized as the sum of the data points, which are the x's, divided by the sample size. So if we take some make-believe population, so here's category X, and we have 5 observations of x's, and these are different measurements. So we measured one individual that happened to be a size of 1, another one that was a size of 2, another one a size of 3, etc. down to 5. Our sample size is 5. Now we can calculate the mean by summing these 5 data points, which add up to 15. And then here we can take that 15, divide by the number of samples, or the sample size, 5, and our mean is 3. Okay, so that describes where the distribution is centered. So next up, we can talk about, well, how do we figure out a way of summarizing how wide or spread out the data are in that distribution? So a way we can think about the spread in data is, here are our 5 data points as before. The mean of these is 3, and we have one that was, the highest point was 5, the lowest one was 1. So if we're graphing these out, here's the mean, and the spread in the data is how far each of these points is from that mean. So hypothetically, we want some estimation of the average distance of each point from the mean. So what we can first do is take each point and subtract it from the mean. So here's each point from this central place. If we have these same points, 1, 2, 3, 4, and 5, we can make a new column that is the mean minus each point. And so 3 minus 1 in this case is 2, this is 1, 0, minus 1, minus 2. So that's how far each one is. However, these ones are negative values, these ones are positive values. We don't care about the direction of difference from the mean, only the magnitude of difference from the mean. So we essentially are going to want to get rid of the signs, and so we're going to take this quantity, x bar minus x, and square it. So this becomes 4, 1, 0, 1, and 4. So just like when we were calculating the mean, we summed up the total and then divided it by the sample size. Now, the formula for variance, and variance is symbolized by s squared. The formula for this is simply the sum of x bar minus x squared over the sample size minus 1. So this is basically saying, aside from the square, it's the average difference of each point from the mean. So how far on average is each point from the mean? In this case, since we've got the square on it, it's the average squared distance from the mean. And we'll talk about that and its relevance in a moment. But to calculate this variance, now all we have to do is sum this column. So if we sum this column, we get 10. And we can divide this column, that 10 divided by the sample size, which happens to be 4. And what we get is the variance is 2.5. Okay, the variance, since it's the squared difference of each point from the mean, doesn't mean so much. So a more typically used and more relevant measure of the spread of the data is the standard deviation, which is symbolized by s, and that's because it is equal to the square root of s squared. So now we're getting rid of this squaring, we're taking care of that, so we basically are getting the absolute value of the difference between each point and the mean. And so to get this, we can take 2.5, take the square root of that, and we get the standard deviation is 1.58. Okay, so now how does that help you distill a big distribution down into a few basic points? So let's take our distribution. We said the center of it is 3, and that's because that is x bar, or the mean. And then plus or minus 1 standard deviation. So this is plus or minus 1 s to either side. Well, what this tells us, it doesn't matter the number of data points in the distribution. It doesn't matter the height of the distribution, how wide it is. The standard deviation is standardized across distributions. It's telling you that if you were to take plus or minus 1 standard deviation, then the area under the curve is going to encompass 60, it's plus or minus 1 standard deviation is going to encompass 68% of the area under this curve. So 68% of the data points in the distribution will fall within plus or minus 1 standard deviation. Plus or minus 2 standard deviations, if you were to go out one more, is going to cover 95% of the area under the curve. And if you keep going one further out, we're covering nearly the entire distribution, and indeed, if you go out plus or minus 3 standard deviations, 99% of the area under the curve is going to be explained. So with just those two numbers, mean and standard deviation, we can describe an entire distribution of individuals. Now, comparing distributions of individuals will come next.